Hello everyone and welcome back to another video here on the Hidden Quantum Champion series. Today we are looking at the company called Mesa Quantum, which is trying to revolutionize quantum sensing by bringing quantum sensors to chip scale. And if you are interested in quantum sensors, different types of quantum sensors, or if you follow up on what is happening in the world of sensing, then today's video is probably interesting to you. And of course, if you like to stay informed about quantum, then not only watch today's video, but also make sure to subscribe to this channel so you don't miss out on the next one. So with that, let's hop right into it. We are looking at Mesa Quantum. And before we do so, maybe a little bit of context, also what always gets me excited about quantum sensing. So my first job after basically graduating with my PhD from the university was actually in a sensing company, not a quantum sensor company, but classical sensors. And the founders had been one of the first people that had made it, that had created a semiconductor-based sensor for temperature and humidity, of course, within the PhD thesis in the lab. And they were going to bring this up to scale, bring this to chips with this company. And this company had evolved into one of the world leaders, if not even the world leader in temperature sensing, temperature humidity sensing. Now, this is a very interesting story because within the company you can see also, I mean, when I worked there, I saw that some of the first samples that looked still very clunky, but they were already, let's say, on a PCB, printed circuit board basis, and they were already proper sensors. And then over the years they had developed these sensors really into, let's say, a big chip scale manufacturing business. And one of the key ingredients into that is miniaturizing the sensors using existing CMOS technology and making them smaller and even smaller so that they can fit into more and more products. And of course, another thing that is actually what got me to learn about this company was that they were also calibrating those sensors in the production. So with that, you can make sure that, okay, and that's across different sensor types that they're selling. These sensors, they are being calibrated. So what you receive as a buyer of those sensors is something that, okay, out of the box does not require, or depending on how you're using it, might still require some recalibration, but it comes already shipped in a way that is working pretty well. And that's, I think, something that is very interesting when thinking about quantum sensors, because why do you actually need to calibrate something, or why do you need to recalibrate it over time? That's because of drift and because of the fact that you are looking at a macro system and that basically requires some kind of calibration. Now for quantum sensor, you might not have this drift because you're looking at fundamental properties. Like, think about the speed of light, right? It's a fundamental property. In the vacuum, it's a fixed number, so it's only constants, it doesn't change. So if you would, for example, build a speed of light measurement sensor, well, actually the speed of light is fixed. So basically, there's nothing to be calibrated, there's nothing to be recalibrated or to drift, right? Everything else can drift, but not the speed of light. So there are other quantum properties that are fundamental, like, for example, charge quantization, that can then lead to other things, like to other sensor related numbers or properties, and that can then help you to kind of make sure that you don't have any drift in the system. But okay, that's the long story out. What is interesting is bringing those sensors to chip scale allows you not only to produce them in a very controlled way, because you're making use of existing semiconductor technology and the chip scaling history that has been built up over decades of years, but it also allows you to go forward and miniaturize your sensor. And why is that important? It's important because it changes the whole price and cost dynamics of your sensor. So if you are able to bring your sensor on, let's say, a chip-based platform, even if you say like it's the whole readout electronics and so on is manufactured in a classic CMOS process, and then on top of that you apply something that basically creates the sensor chip out of it, like you put the sensor cell on it. Even with that, you are still using the power of semiconducting technology, the power of what has been built over decades in terms of semiconductors, and you're building on top of that. So you have a very interesting cost dynamics, and you can scale this up. So up to now, maybe quantum sensors are only interesting for labs. Then usually you have the national labs that are using them for standardization, right? Like there has been some efforts in replacing atomic clocks with new types of sensors and so on and so forth. And as you kind of make them better and better in terms of productionalizing the process of creating those sensors, you also change the cost dynamics. They become cheaper and cheaper, all the way to the point where at some point they might end up in your smartphone. Of course, I'm not saying that quantum sensors will end up in your smartphone tomorrow, and I'm also not saying that Mesa Quantum is going to make this possible, but it might be, right? And that's where it becomes interesting, because once you have these types of sensors in these new applications, you can also think again about like new scaling, new applications that are becoming enabled. And of course, on top of these sensors, there's a whole ecosystem of stuff that is growing, right? So inside your smartphone, you have an acceleration sensor that is being, for example, used to identify whether you tilt your smartphone or whether you put it in like horizontal versus vertical. But you can also think about other things. For example, I know somebody who built a very interesting physics app on that. And you can, for example, jump into an elevator, and then it uses the acceleration sensor to actually measure the acceleration within the elevator and then calculate from that back, for example, the height distance that you've been going up. You can also combine it with the pressure sensor inside your phone, and suddenly you have something that is maybe interesting for indoor navigation. So there are many, many new applications that are coming up when you enable these sensor platforms. But that was a very long opening. Now let's really jump into Mesa Quantum and learn what the company is building and how that is interesting for all of us. Okay, so here we are on their website as per usual. It says Mesa Quantum and then chip-scale quantum sensors engineered for industry. Mesa Quantum is commercializing chip-scale quantum sensors to meet the demands of industry. These high precision instruments will be the key enablers for the next generation of tech innovation. By taking chip-scale quantum sensors out of the lab and putting them into the hands of real product developers, we are engineering quantum tech for practical applications. And then moving on, our disciplined engineering practice pushes the bounds of what's manufacturable at scale. We will build the products that the market demands. We perform in iterative engineering cycles and focus on more than just optimizing performance for academic research. The market needs a cost-effective solution. Our industry partners need reliable sensors with low size, weight, and power consumption, and lots of them. Okay. And then here we see some of the applications that I guess they are targeting. So quantum sensors for alternative PNT, the GPS alternative. So short for this. All these carousels are way too fast. Short for alternative position navigation and timing. Alt PNT tech is urgently needed as backup for GPS. Many technologies our society depends upon are reliant on GPS, which has been declared a significant single point of failure in our country by the National Security Council. GPS is vulnerable, and if something were to happen to it, the consequence would be catastrophic. Mesa Quantum Technologies provides more resilient, precise, and scalable methods for synchronization, positioning, and measurement. Maybe a quick note on GPS. So how does it actually work? I'm not going to explain the whole details about it, but basically you are using satellites, or you have satellites up in the sky that are sending some signals down, and now you are basically using your car or your navigation system to receive those signals, and then using timing, you can basically triangulate between those different signals and thereby identifying which position you are in. It's very, very interesting. It also needs a lot of physics into it. Of course, you have satellites that you need to get up into the orbit, but you also have, for example, Einstein's relativity theory, which you actually need to be able to calculate properly your distance or properly your position. But of course, GPS is in a way vulnerable because you need those satellites. You need to be able to collect those signals from the satellites, and you also need to kind of own the satellites. So if you, for example, rely on somebody else's satellites, they can very easily reprogram those satellites to send you some wrong locations, and suddenly your whole navigation is off, right? Or if there was a attack of one of those satellites and then basically it wouldn't work anymore, or a couple of those satellites and they wouldn't work anymore, then of course you would have another issue. So there are various different reasons why GPS is in a way fragile or is prone to be, or could be a target to be attacked, right? And GPS is of strategic importance for, of course, the whole defense trajectory, but also, again, a lot of civil applications rely on that, right? So if you hop into your car and you turn on Google Maps or Apple Maps or your navigation system that comes delivered with your car, that is going to use GPS to actually navigate you around. Now, thinking about, I don't know, autonomous vehicles, there was also for a long time a discussion whether GPS should play a role in making the vehicle navigate. I think this is currently not so much anymore a topic because you're using a lot of optical sensors, radar, lidars, and so on to actually map your surroundings and thereby be able to find the right position, the right lane for the vehicle to go on. But for a long time also there was a discussion if there should be something like an ultra precise GPS that the self-driving car can use to know exactly where the lane is. Now back to the text, right? So those satellites are vulnerable to electronic attacks such as jamming and spoofing. I don't know where I was. I think it was this one here, right? Spoofing. And countries like China, Russia have demonstrated anti-satellite weapons capabilities that could shoot them out of the sky. During a GPS outage, any smart technology would be blind. The US Department of Defense takes this threat seriously, so chip-scale quantum sensing for alt-PNT is a national priority. Equipping our industrial base with essential tech is our primary short-term objective. As a dual-use technology, quantum sensors have massive long-term implications. Alt-PNT will prove crucial for autonomous systems like self-driving cars, robotic workforces, smart energy grids, deep-sea exploration, small satellite constellations, and more. Mesa quantum sensors will be a key player for future innovation. Okay. So design for today's applications. Here are the target applications for these types of sensors, right? So when we're talking about position sensors, there's resilient navigation, data networks, and that comes to this whole timing question that I've been touching briefly upon. The same is true for communications. There's something about remote sensing here, satellites. I guess that's similar to the GPS topics we talked about before. GIS, so geographic information systems, autonomous systems, we've also briefly talked about that, and financial markets, of course, again, the timing topic, right? When we talk about high frequency trading, timing plays an important role. So vapor cells, the heart of quantum sensors, that's now on the technology of it, right? Vapor cells, maybe very, very briefly a step back on vapor cells. So when I studied physics in university, there were vapor cells already as demonstrators for quantum particles. So the sun is permanently emitting particles into all of different directions, also in the direction of Earth. And in the old days, when there was no computer technology, people were actually using so-called vapor cells. So what are these vapor cells? You create an environment where you have a vapor of a specific chemical in there, and you hypersaturate that. So basically, like a cloud before it starts to rain, it's a highly saturated vapor situation. And now if you put something in there, like some disturbance, it will immediately collapse into the liquid state again, so it will start to rain. Now, when you have, and that's the idea of rain seeding, right? So where you take airplanes and you spray some chemicals in the air, and then suddenly the clouds start to rain. That's at least the idea. Now for these vapor cells, the idea is that, okay, if you have a cosmic particle that interacts with this vapor within the cell, it will basically start to collapse the vapor. So you will see that there's something happening within the vapor cell. And in fact, you can really see those. And if you now put a magnet behind, you can see that some of these particles, they are electrically charged, because if you think about electric energy in magnetic fields, you have the Lorentz force, so-called Lorentz force. So electrical charges will be put on circular what is it called, trajectories, and because they are losing energy, it will be more like a spiral, like a vortex. And then you could even measure the electricity that was associated with those particles, or the speed that was associated with those. And in fact, in the old days, people were using these vapor cells and they were taking photos of it. And then you would have people that went through all of the photos and collect the ones with the events on it, and thereby analyzing and doing particle physics. Now here, as far as I understand, the idea is to use this old idea of vapor cells and transform that into some type of quantum sensors. But let's dive into what Mesa Quantum is giving us in terms of information here, again with a very fast moving carousel. So let's try to read this. So vapor cells are tiny glass containers filled with a cloud of vaporized alkaline metal atoms. We shoot laser light through the cell, and a photodetector on the other end detects the percentage of light makes it through versus what percentage was absorbed by the atom cloud. When the vapor is subject to outside disturbances like magnetic fields, acceleration, and so on, the atom's internal quantum state change. One way to conceptualize this effect is to visualize the cloud's opacity changing. The more opaque the atoms, the less light hits the other side. We take that data, the ratio of photons fired to photons received, and match it up to the math. From this data, we then determine the magnitude of the disturbance we are measuring. We can use the same method to make an atomic clock, except in this case, we try to keep the atoms perfectly isolated from outside disturbances. We can then use the intrinsic oscillations of the atom states to create an extremely accurate time reference. So, okay, now we understand we are using these alkaline metal atoms. They are within this vapor cell. You shoot laser light on it in a very, let's say, well-known fashion. So you know exactly how much light goes in, and then you measure how much light comes out. And this is a very, let's say, classic spectrometry kind of setup for a sensor. So you have some medium in the center, you have a light source, you have a detector, and then you're measuring the change of light going through as a function over time, or changing outside effects, and thereby you are, let's say, calculating back on certain sensing property. The same is being done, for example, with gas sensors. Most of the gas sensors today, you have a light source, you have a detector, and you're measuring basically the change of absorption of this light, and that will tell you something about the gas concentration. At least this is one way of measuring gas. There are other ways as well. They are explaining this can be used to measure things like acceleration, but you can also use it if you kind of isolate it pretty well to build something like a clock. So types of quantum sensors in our roadmap. First one is atomic clocks, so precision timekeeping for clock synchronization in GPS denied environments. So defense application. Then we have the gyroscopes, so basically measuring accelerations, right? Orientation and angular velocity measurement for stability control and autonomous navigation. Could also be interesting for airplanes, could be interesting for submarines, where generally the navigation is a bit more difficult because you usually don't have a very well connection to GPS if you're way below the sea. Then you have the magnetometers, so measuring magnetic fields, right? This is interesting for medical imaging and consumer electronics, but it's also interesting for navigation because the Earth has a magnetic field that is changing over time very slowly, but it is existent, and you can actually measure local variations in this magnetic field. So we always say the Earth is like a magnet, and you have the compass that is showing in one direction. But actually, if you were to measure the magnetic field, you would see that it has some fluctuations in it, and that has something to do with the Earth's crust, or basically with with how the Earth looks on the inside, right? Because if you have a lot of metal, for example, if you have a lot of iron below you, that might get magnetized over a while, and then you might have some stronger magnetic field, so it amplifies, whereas in other cases it might be weaker. And you could use these local variations to build an alternative navigation system, so something like a magnetic map of the Earth, right? Then you have the Rydberg atom radio frequency sensor, so RF field measurement of a huge frequency range for the next generation of radio antennas. Then gravimeters, so gravitational field sensing for submarine navigation, earthquake prediction, and subterranean surveying, so basically for mineral exploration as well. And there has been some videos of myself highlighting some of those companies in those different fields in the past. So if you haven't watched them, make sure to go after this video, of course, check out our YouTube channel's playlist, which is the Hidden Quantum Champions playlist. In there you find all the videos, including, for example, I think it was Nomad, who is making sensors for gravity based on quantum technology. Then we have the accelerometer, so qualifying changes in velocity for autonomous navigation and consumer electronics. Quantum sensors are so reproducible, low cost, small size, lightweight, low power consumption, and reliable. I'm not going to go through all of this now because otherwise this video is getting too long. And then we are translating physics into revenue. Okay, says the CTO of the company. Then recent news. So I'm recording this in May of 2026, and the last one is here from April, which says Mesa Quantum at SPIE Defense plus Commercial Sensing 2026. So I would say it's very much up to date in terms of latest news. Then, as per usual, we have a way to reach out to them and some information about them being based in Boulder. I guess this is Colorado. Not sure. I'm not so good in geography, as you can see. Let's quickly take a look. Okay. So I think that's already it. So then we are already at the end of today's video. Okay. As per usual, thank you very much for listening all the way to the end. It was a pleasure to look together into Mesa Quantum. If you don't want to miss out on the next video, make sure to subscribe to the channel as per usual. Stay hydrated and see you in the next one. Bye bye.